we'll get started. Thank you for sticking around. I appreciate that very much. Thank you. And anyone else that's interested, please, there's plenty of seats, of course. So my name is Ty Smith. I'm with a company from the United States called Paragon. Oh, up higher? Okay, so I'm from a company from the United States called Paragon. We supply a lot of different components to the nuclear industry, both in the United States and then worldwide, globally. I'm going to talk today about Paragon, what we do a little bit, and then I'm going to talk about some of our capabilities in integrating reactor protection systems and INC systems for next generation reactors. We see that as a topic that, especially for advanced reactors, thinking about the next generation of sensors and how we will improve the reliability and the performance of those designs. So let me talk just a little bit about who Paragon is. And so I'm going to, our mission is to be the nuclear industry's most trusted supplier, which is no one's throwing anything because there's a lot of suppliers that are out here. And to us, that really, we start our day with our team at Paragon thinking about how best to serve our customers. And that may mean some different things to some different customers. But trust is important because if we do not perform well, for our customers, we're not going to have a lot of success. And if we don't have success, our customers don't have success, and we ultimately don't change the climate and improve the energy production of the world, which is really what we're trying to do. We do we become more trusted as a supplier by thinking about things a little differently. So being more collaborative with our customers, going to the root cause of the issues that they're having. If they're having issues with noise, or maybe they're having issues with obsolescence, what is the root cause of those problems? How do they solve them on a programmatic level so that they don't happen again? Instead of just troubleshooting individual problems, how do we think about those challenges globally? And then innovation has a lot of different meanings in our industry. We've innovated the ways that people purchase parts in the United States, but we're also innovating how they integrate those parts together. And so you have to have different solutions for different problems. So let me talk just a little bit about who Paragon is, because you might not have heard of that name before. And the reason is that we're actually 5 different companies that have come together under a common brand name that we started in 2017. So we actually began in the year 2000 with a company called ATC. We then acquired 2 other companies, one in Schenectady, New York, called Spectrum Technologies, that had done a lot of work on motor control centers and instrumentation and control equipment repair. We then acquired a company in Oak Ridge, Tennessee, which is where I'm from. So I grew up in Oak Ridge, Tennessee, if you're familiar with that area. And then we became a company called ATC Nuclear, which you may know over the years, primarily a US-based supplier. In 2017, we had a really important change. We bought the company from the corporate parent, so it was purchased by the management team from ATC. We became Paragon, which is the new company name that you see today. And then we've continued to acquire new and additional capabilities. So we purchased a company called Nuclear Logistics. It was owned by AZZ. We did that in February 2020, right before COVID-19. So it's a good time to buy a company, of course. And then we bought another company just last month called Technology Resources. Their president is a gentleman named Ted Quinn, who worked with a number of people out in the supply base on IEC standards and IAEA standards as they apply to nuclear instrumentation. So let's talk a little bit about what Paragon does as our core business. So we've got about 230 people. About 95% of our work is in the nuclear industry. So it's very focused on the challenges that accompany the nuclear industry. And because of that, we have all of the expected QA quality assurance capabilities. So that includes NQA1 as an Appendix B supplier. for 10 CFR 50 Appendix B in the United States. And then in Canada, we have an important designation as 299.1, which means we've qualified ourselves as an engineering house to do first-of-a-kind designs for next-generation reactors. So that's an important differentiator for us. And most of our work in the U.S. has been focused around challenges with obsolescence. And you can see, if we've got the pointer working here, it doesn't work on the screen. So obsolescence is a huge problem in the U.S. It's a huge problem at most nuclear power plants globally, and it's a growing challenge, particularly for European plants as they age. And if you look around the wheel that we have here, all of these solutions are designed to help our customers manage their obsolete components. And it starts, it goes around clockwise depending on the level of complexity. One of the innovative programs we started in the United States is a program we call Rapid Response, where we help nuclear power plants buy and sell parts between each other. So about 3,000 transactions a year occur between U.S. plants that are owned by different companies. They are selling inventory that they have on hand to other U.S. reactors so that they help monetize those assets, and the other customer can continue to operate. So we've seen that business growing, and we go all the way around to doing INC repair, so instrumentation control equipment repair, commercial grade dedication, reverse engineering, equipment qualification, which I'll talk some more about, and custom design. So specific to in-house testing capabilities, we've got the whole gamut of IEEE 323 and 344 testing capabilities, seismic capabilities. We had done the LOCA and the high energy line break testing for the AP1000. So a lot of capabilities to test the equipment prior to installation in the plants. And we do that as an integrated package. All of that happens within one facility in our Fort Worth, Texas location, so that there are not issues with transporting equipment that has been maybe seismically tested to another location and then trying to see if it's still working. It's important to have all of that under one roof. And then we also do the modifications to that equipment so that it will pass. So if there are commercial components that are having difficulty passing perhaps the EMI RFI testing, we can add filtering and other other technologies that prevent it from being so sensitive to noise. So in summary about Paragon, we're a combined entity of 5 different companies. We've been around for about 20 years and have a lot of different capabilities, and all of the U.S. plants are our customers, but we also have customers across the world. So now let me switch topics a little bit and talk some real specifics about integration of field sensors into reactor protection systems. I feel like this is a little bit of inside baseball, to use a term from the U.S., because we're going to talk some about some real specific problems with new or with existing plants as it pertains to how you integrate field sensors. So the example I'm going to use today is a neutron flux system. So if you're familiar with nuclear power plants, we measure neutron flux from startup to shutdown. It's an important indication of reactor power. It's an important variable outside of flow rate and pressure and temperature. Neutron flux is the 4th primary variable that we use in nuclear reactors. And we have a system that operates across 11 different decades of power, and we've designed that system to be as universal as we can as we come into the age of advanced reactors with some unique needs and some very different needs from light water reactors. And so but it gives us an opportunity to think a little more collaboratively and innovatively about the solution. And we've been able to do that in the most recent example of our system, which is being deployed to the SHINE research, or the SHINE medical isotope reactor that's being built in the United States. So importantly, we are doing all of the signal pre-processing in analog electronics, which it makes it easier to, particularly in the United States, to integrate the technology. There's less cybersecurity risk. So all of those things help us to license that technology for use. But we're also bringing the reactor protection system back into the neutron flux monitoring system amplifier cabinets so that we capture the signal as close to the source as we can. And so we can operate that as an analog solution only, if that's the licensing basis that the plant would desire. But we can also integrate that into the reactor protection system. Let me show you what that looks like. So in this example, our partner Rock Creek, they are the developer of the reactor protection system for the NuScale plant. They developed a FPGA-based platform called HIPS. It's the highly integrated protection system. And that system has a modular deployment, so it's relatively easy to take different parts of it and deploy it in some different areas. And so what we designed for our customer at Shine is the ability to take the card that would normally be in the reactor control room, so you would run all of the neutron instrumentation cable all the way to the reactor control room. In some cases that could be 300 meters of cable. It becomes quite difficult to manage. It is a source for noise and other issues. We actually took the reactor protection system field module called the input submodule from where it would normally be in the control room and moved it all the way out into in the containment area so that it would be locally deployed. And that allowed us to digitize that neutron flux monitoring system early in the path of the signal, which it has a lot of benefits I'm getting ready to go through. But most importantly, it takes and extends the reactor protection system boundary all the way out. So it's covered by the same licensing basis, covered by all of the same common cause failure analyses. So it works very well in that environment. So what are those benefits of that type of approach? So you can apply this type of extension of reactor protection systems into the plants across most of the safety-related field sensors that you see deployed today, whether that's a pressure measurement, a temperature measurement, maybe it's a movable in-core probe system. All of those things we can do the same methodology and actually move the reactor protection system boundary out further into the field environment. And that gives us the four different capabilities that I'll list here. One is that if you work in a nuclear power plant today, you have some problems probably with noise. So it's electromagnetic and radio frequency interference, particularly if you're running cables next to large motors. And maybe you've tried to install some variable speed drives that cause a great deal of noise. It can induce noise on systems that didn't have noise before. So some of the upgrades that you've done to your plants might have increased the noise output of all those systems. Because we take the analog signals and digitize them earlier in the path, we're able to basically move a 485 base signal along a twisted shielded pair. Is virtually noise immune up to millions and millions of volts before you have problems with those type of digital signals. The second large benefit, particularly for advanced reactors that are looking to minimize the size of their footprint, is that you can have a significant space reduction by removing the electronics that take in the field sensors, moving them further into the field. You remove all of those field sensor cables that come up into the reactor control system, maybe from the 4 to 20 loops, your 0 to 10 volt loops. All of those components that come into modern, today's reactor protection systems, we're able to move those into a digital transmission early in the process, and we're able to put that onto the same digital backplane that the reactor protection system is operating under, so that you can reduce the number of cables. So maybe what was once a cabinet full of equipment will be reduced to just a handful of twisted shielded pair cables. We're also able to eliminate the need for new digital devices. So as advanced reactors and small modular reactors look to suppliers out in the industry for field sensors, a number of those field sensors have their own digital components that are a part of that. and it introduces new common cause failure evaluations and other digital failure evaluations, cybersecurity vulnerabilities into the plant. If you can eliminate the need for those field sensors to have those digital components and integrate them into the RPS as an analog signal, you can remove those challenges. And we take advantage of the already licensed digital platform to integrate the field sensors. It's a much more, it's a smoother transition into the reactor protection system. And the final important capability that we've been able to add, particularly to neutron flux monitors, is the ability to do online calibration. So we've programmed all the amplifier electronics with a digital pot, so you're able to tune the electronics from the control room on a separate communication bus. All of that's done through a maintenance workstation, and all of it falls under the already licensed reactor protection system of Rock Creek, instead of having to have a separate calibration system for those different field sensors. So those things, when you combine them together, give us a lot more flexibility on the reactor protection system. It gives us a much smaller footprint for the control rooms, ultimately reducing the cost of the reactor as the volume of safety-related components, particularly in the reactor control room, is significantly reduced. So at this time, I'll take any questions that you guys have. But in summary, we work to collaborate with our partners in a lot of different ways. But, most importantly, I think you have to think about the needs of the new reactors in a different way than we've thought about the needs of light water reactors. And that's one of the things that we're focused on for the future. So that's all I have. Thank you. Any questions? Yeah, go ahead.